Differentiation of inverse trigonometric functions. Suppose the derivative of the function y equals f of x is equal to dy dx equals f prime x. Now suppose the inverse function is the inverse function of x. So f to the power minus 1 is the inverse function. We can find the derivative of the inverse function by rewriting and using implicit differentiation. So if we have y equals the inverse function of f of x, then applying the function to both sides, we'll end up with f of y on the left, and the inverse function of f and the function f will cancel out, and we'll be left with x on the right. So we have f of y equals x, so f prime y dy dx is going to be equal to 1. Because we're going to differentiate both sides with respect to x. So since we don't have an x on the left, we stick on a dy dx. So really you're applying the chain rule here. And if you're unsure of that, go back and have a look at the implicit differentiation video. And differentiating with respect to x on the right, we just get 1, because the derivative of x is 1. So we have f prime y dy dx equals 1. And now solving for dy dx, we get the dy dx on its own, and we get 1 over f prime y. So we divide by f prime y to get the dy dx on its own. So basically, to summarize, if y equals the inverse function of f of x, then dy dx equals 1 over f prime y. This theory can now be applied to the problem of finding the derivatives of the inverse trig functions. Y equals the inverse function of cos x, y equals the inverse function of sin x, and y equals the inverse function of tan x. The derivatives of these functions are given in the following form on page 25 of the formulae and tables. So here we have our functions, and here we have our derivatives. In practice, it's best to only use these when a is equal to 1. So x over a, so x being 1. So the inverse function of cos x, or the inverse function of sin x, or the inverse function of tan x. So when the a is 1, so basically when you have x over 1, which is just x. So for example, d inverse function cos x dx is equal to minus 1 over root 1 minus x squared. So we can see that if we have cos, the inverse function of cos, and we have x over a, or in this case the a is 1, we have minus 1 over root a squared minus x squared. So basically that a squared becomes 1 squared, which is just 1. If we have d inverse function of sin x dx, we get 1 over root 1 minus x squared. So sin x here is really x over 1. So for the inverse function of sin x over 1, which is just x, we have 1 over root a squared minus x squared. So the a squared becomes 1 squared, which again is just 1, and we already had 1 on the top. And then for tan, so d inverse function tan of x dx, we get 1 over 1 plus x squared. So again, here's our tan formula. So the inverse function of tan x over a. So x over a being x over 1, which is just x. We end up with a over a squared plus x squared. So we'll have 1 over 1 squared plus x squared. So 1 over 1 plus x squared. However, if the function exactly matches the inverse function cos x over a, the inverse function of sin x over a, or the inverse function of tan x over a, where a is a constant, then it is safe to use the formulae in the tables. So here we have page 25 of our formula book, and here we can see our 3 inverse trig formulas. So we have our function on the left and our derivative on the right. If y equals the inverse function of sine of x, show that dy dx is equal to 1 over root 1 minus x squared. So if y equals the inverse function of sine of x, then what we do is we swap the x and y, and we change the inverse function of sine to sine. So we get sine y equals x. So what you're doing is you're applying the function of sine to both sides, and that cancels out the sine to the power minus 1, which is the inverse function of sine. So using implicit differentiation, cos y dy dx is equal to 1. So sine, the derivative of sine is cos, or the derivative of sine y is cos y. And then we stick on a dy dx because we're using implicit differentiation. And because dy dx means differentiate with respect to x, and since for sine y we don't have an x, we stick on dy dx. So this is basically the chain rule. So for a reminder of where this comes from, have a look back at a video on implicit differentiation. But basically, if you want to differentiate with respect to x and you don't have an x, you differentiate anyway, and then you just stick on a dy dx. And then the derivative of x with respect to x is 1. So now we have cos y dy dx equals 1, and we're going to solve for dy dx. So we need to divide both sides by cos y to get the dy dx on its own. So we have dy dx equals 1 over cos y. Now cos y we can rewrite as the square root of 1 minus sine squared y. And this comes from our identity cos squared y plus sine squared y equals 1. So cos squared y equals 1 minus sine squared y. So cos y equals the square root of 1 minus sine squared y. So this is one of our trigonometric identities from our formula book. So this gets swapped for this. And then we just rewrite using sine y in place of x. So we said here at the start that sine y is equal to x. So therefore sine squared y we can swap for x squared. So now we have dy dx equals 1 over root 1 minus x squared, which is what we wanted. So here we have an alternative method. So y is equal to the inverse function of sine of x. Then sine y is equal to x, so we know this already, so we're just rewriting. These two equations are equal, we're just rewriting them. So sine y is equal to x, so therefore it's equal to x over 1. And we know sine, in terms of SOHCAHTOA for our trig identities, sine y is equal to O over h, the opposite of the hypotenuse. So the x must be the opposite, and the 1 must be the hypotenuse. So the opposite is equal to x, and the hypotenuse is equal to 1. So we can draw a right angle triangle. We label our angle as y. The opposite is x, and the hypotenuse is 1. We don't know what the adjacent is at the moment. And then we're going to label it a, b, and c using Pythagoras' theorem. So the c must be the longest side, the hypotenuse. So Pythagoras' theorem states that c squared equals a squared plus b squared. So we have 1 squared equals a squared plus x squared. So we rewrite in terms of a. So we have x squared equals 1 minus x squared. So a is equal to the square root of 1 minus x squared. So now we have a, our adjacent, so we can label it as root 1 minus x squared. The opposite is still x, and the hypotenuse is still 1. So let's go back to sine y equals x. So we want to find the derivative. So we're going to use implicit differentiation. So the derivative of sine y is cos y. Since we're differentiating with respect to x and we don't have an x for sine y, we stick on a dy dx, so this is our implicit differentiation. And the derivative of x with respect to x is 1. So we have cos y dy dx equals 1. So again, from the triangle, we stated that cos y is equal to root 1 minus x squared over 1. So that comes from Ka, from SOHCAHTOA. Cos is equal to the adjacent over the hypotenuse. So the adjacent is root 1 minus x squared, and the hypotenuse is 1. So cos y is root 1 minus x squared over 1, which is equal to root 1 minus x squared. So we used implicit differentiation to say that cos y dy dx is equal to 1, so I've just written it again down here. So we're swapping the cos y for root 1 minus x squared, because we worked that out over here. So we have root 1 minus x squared dy dx equals 1. So solving for dy dx, we get 1 over root 1 minus x squared, which is what we worked out already. So you can use this method or the method in the previous slide to show that dy dx is equal to 1 over root 1 minus x squared. Find dy dx if y equals the inverse function of sine of x over 4. So we can use the formula from the tables with a is equal to 4. So our formula from the table states that the inverse function of sine of x over a is equal to 1 over root a squared minus x squared. So if y is equal to the inverse function of sine of x over 4, then dy dx is equal to 1 over root 4 squared minus x squared. Like other basic functions, the inverse function of sine of x and the inverse function of tan of x can occur in products and quotients. Find dy dx if y is equal to 3x squared minus 1 tan inverse function tan of x. So our 3x squared minus 1 is going to be our u, and the inverse function of tan of x is going to be the v. So we use the product rule. If y is equal to uv, or u multiplied by v, where u equals u of x and v equals v of x, then dy dx equals u times dv dx plus v times du dx. So the given function is a product, so we use the product rule. So we swap the u for 3x squared minus 1 with brackets. We swap dv dx for 1 over 1 plus x squared. So if we have the inverse function of tan of x, then our derivative is a over a squared plus x squared. And our a is going to be 1 because x is really x over 1. So we have 1 over 1 plus x squared. Then we have a plus. Then our v is the inverse function of tan of x. And then du dx is going to be 6x. The derivative of 3x squared is 6x. Then we simplify. 3x squared minus 1 multiplied by 1 is 3x squared minus 1. And then our denominator will be 1 plus x squared plus the 6x comes in front, inverse tan of x. The chain rule for inverse trigonometric functions. The chain rule must be used to differentiate inverse trig functions of the form y equals cos inverse u, y equals sine inverse u, or y equals tan inverse u, if u is anything other than exactly 1x. So for example, we would need the chain rule to differentiate sine inverse function 2x, tan inverse function 3x plus 1, or tan inverse function 1 over x. Suppose y equals sine inverse function u, then by the chain rule, dy dx equals d sine inverse u dx, which is equal to d sine inverse u du multiplied by du dx, which is equal to 1 over root 1 minus u squared multiplied by du dx. Because we know the derivative of the inverse of sine is 1 over root 1 minus x squared, but in this case it would be u squared. And then we multiply it by du dx. So this is using the chain rule. And cos inverse u and tan inverse u can be approached in the same way. So chain rule 3 is our inverse trig functions. So d cos inverse u dx is equal to minus 1 over root 1 minus u squared times du dx. And d sine inverse u dx is equal to 1 over 1 minus u squared du dx. And d tan inverse u dx is equal to 1 over 1 plus u squared times du dx. i.e., differentiate the inverse trig function, keep the value, and multiply that by the derivative of the value. Find dy dx if y equals tan inverse 4x plus 1. So our solution is y equals tan inverse 4x plus 1. So we let the 4x plus 1 be 4x plus 1 over 1. So where a is equal to 1. And we're going to differentiate the trig function, keep the value, and multiply that by the derivative of the value. So dy dx is equal to 1 over 1 plus 4x plus 1 squared multiplied by 4. So the 1 over 1 plus something squared comes from here. So if we have tan inverse and we have something over 1, so that something is the x, so we have tan inverse x over a. So the x is 4x plus 1 and the a is 1. Then the derivative of that is a over a squared plus x squared. So remember the a is 1. So we have 1 over 1 squared plus x squared. So we have 1 over 1 squared plus x squared. But the x in this case is 4x plus 1. And we're going to keep the value. So we have 4x plus 1 in brackets. So we differentiate the inverse function, so that's the blue part. And then we keep the value. So we keep the x, which in this case is 4x plus 1. And we multiply that by the derivative of the value. So the derivative of 4x plus 1 is 4. So this part here is how we differentiated the tan inverse. And the 4 here is how we differentiated the value. So then we just tidy up. 1 multiplied by 4 is 4. And then our denominator stays the same, 1 plus 4x plus 1 squared. So we differentiated the inverse function, we kept the value, and we multiplied that by the derivative of the value. So this is basically the chain rule. It's another way of saying the outside multiplied by the inside. So the derivative of the outside, keeping the value, multiplied by the derivative of the inside.